Welcome back to the course Modeling Combustion with Answers Fluent offered by EDAL Systems. In today's class, we will discuss about partially premixed combustion model. So we'll discuss what is this model and what are the steps involved in modeling such kind of problem. So till now we have discussed premixed combustion and non-premixed combustion and how these two combustions vary. So partially premixed combustion is combination of both premixed and non-premixed systems because these systems are premixed flames with non-uniform fuel oxidizer mixtures, and so this model is also a combination of non-premixed and premixed combustion model. So when we have premixed jets discharging into a quiescent atmosphere or a system with lean premixed combustors with diffusion pilot flames and or cooling air jets, then we can use this partially premixed combustion model of fluid to simulate such kind of problems. So how these two models are combined together into a one model, that is partially premixed combustion model. So the strategy is straightforward. That is, the reaction progress variable C is used to track the location of the flame, which we call as flame front. Then before the flame front at C equals to 0, the mixture is unburnt and the mass fraction and other variables are computed using pre-computed mixture fraction PDFs. Whereas inside the flame, a combination of the two models is used. In the burnt area, that is at C equals to 1, the equilibrium mixture fraction is computed. So this way we can simulate a partially premixed system using partially premixed combustion model offered by ANSYS Fluent. The key features of this model. So ANSYS Fluent offered two types of partially premixed combustion models, that is thin flamelet model and flamelet generated manifold. So in thin flamelet model, it assumes that the premixed flame front is infinitely thin and that within the flame brush, the thermochemistry is described by a linear combination of unburnt and burnt mixtures. Whereas in flamelet generated manifold method, it assumes that the thermochemistry states in a turbulent flame are similar to the states in a laminar flame, and it parameterizes these by mixture fraction and reaction progress. So one have choice of using any of the model from both. Then there are some limitations of this model as well, that the single mixture fraction approach is limited to two inlet streams, which may be pure fuel, pure oxidizer, or a mixture of fuel and oxidizer. Then the FGM model which we discussed is only limited to C equation partially premixed model. So if one is using the FGM method, then they are limited to use C equation model only for calculation of turbulent flame speed. Next, we will see the steps involved in modeling partially premixed combustion model in ANSYS Fluent. So these are the 6 steps which one has to follow when they are carrying out the simulation for the partially premixed systems using this model. So we will discuss each of the steps in detail in further slides. So let's start the first step, that is we have to enable the partially premixed combustion model and we have to set the related parameters. Then we have to generate a PDF lookup table. So when we have enabled our turbulence equation, then we have to go into species and we have to enable the partially premixed combustion model. Then there are other options like inlet diffusion, compressibility effects, etc. One can follow any of them. And as we saw in non-premixed combustion modeling, we have to set the chemistry, we have to set boundary parameters, control parameters. Then we have to calculate the PDF lookup table. Same thing we have to follow here, just that this model is combination of both premixed and non-premixed. Some of the parameters will be included in model setup and some of the parameters will be included while we set up the boundary conditions. So we have to specify our boundary species and their composition in mole fraction or mass fraction, the temperatures of the streams through which air and fuel will be entering. And then we have to provide, if we are using any flamelet model, then we have to specify those parameters as well. In tables, we have to calculate our PDF table. Then comes the third step, that is we have to define the physical properties for our unburnt mixture in the domain. So what ANSYS Fluent will do is that it will automatically select the pre-PDF polynomial function for laminar flame speed, indicating that the piecewise linear polynomial function from the PDF lookup table will be used to compute the laminar flame speed. Earlier in premixed combustion modeling, we have seen that laminar flame speed and turbulent flame speed are the main parameters when we are dealing with the premixed combustion problem. So one has to determine both of these flame speeds in order to analyze the premixed combustion results. So same here, to calculate the laminar flame speed, the PDF table which we just calculated, ANSYS Fluent will automatically select this pre-PDF polynomial function for our laminar flame. So based on what mixture fraction we are using, PDF table will calculate a polynomial function for the variation of mixture fraction versus laminar flame speed. So when we enter into materials under laminar flame speed, we can see that the PDF polynomial function is already defined and we can go with that. Otherwise, one can select a constant value or a user-defined function according to their problem. Then comes the fourth step, that is setting the boundary conditions. So here one has to be very careful while setting the boundary conditions, because here we will be setting boundary conditions for premixed as well as for non-premixed combustion model setups. That is, for pre-mixed flows where unbound mixture will be defined with the progress variable C equals to 0, and for burnt mixture which will be present at outlet, there we have to define C equals to 1. So this will give a range for the flame front for unburnt and burnt mixture. Then we have to specify our fuel concentrations which we just defined in our model setup, that is mole fractions in our boundary species. So we have to specify the mean mixture fraction and its variance at our fuel inlet position. So these all things will be set up in the boundary conditions, and one has to be very careful when they are setting up this boundary conditions, because even if one step is missed, then the combustion won't be initiated and the flame won't be visible. So the next step after setting boundary conditions is to initialize the value of progress variable. So a better initialization is to patch an initial value of 0, that is unburnt mixture, upstream of the flame holder, and a value of 1, that is burnt, in the downstream region once the boundary conditions are specified. So this initialization will help in patching value of C equals to 0, because if one is dealing with a bigger domain and a complex problem, then this patch will help in maintaining an order for the burnt and unburnt mixture. So once everything is set up, then we have to go and we have to solve the problem. While solving the problem, one has to carry out a cold flow simulation first, and then they have to go for the hot flow. Otherwise, they won't be able to patch proper values of C if both hot and cold flow simulations are solved at a single time. So even in post processing, here we can generate graphical plots or alphanumeric reports of the following terms. So here what all things we saw in premixed combustion model and non-premixed combustion model, same parameters we can analyze in partially premixed combustion model for post processing. So next we will see a demonstration for partially premixed combustion model using an example. So here we will define a problem statement, and then we will go into Fluent GUI and we will perform each of the steps which we just discussed step by step, and we will carry out a simulation. Then we will analyze the results using post processing. So let's begin. So this is the problem statement we'll be discussing for partially premixed combustion model. Here we have this 2D domain in which we will be having two inlets, that is air inlet and fuel inlet. There will be a co-flow. So from fuel inlet, we will be sending fuel at a swirl velocity of 30 meter per second. So that will help in mixing of these two fluids. Then this region, and this region will act as walls. This will be axis, and then this will be used as outlet. So air inlet will have 650 Kelvin of temperature from where the air will be entering, and fuel will be entering at 300 Kelvin temperature. And the simulation will be carried out at 0.8 stoichiometric ratio, that is at a lean combustion simulation will be generated. So based on 0.8 stoichiometric ratio, there will be a considerate amount of mass fraction for CH4, N2 and O2, which will be used as reactants for our simulation, and that can be calculated using a chemical reaction. When we write a chemical reaction, then based on our stoichiometric conditions, we can calculate our mass fractions for our reactants as well as for our products. So we will simulate this condition in ANSYS Fluent GUI, and we will understand how we can combine this premixed and non-premixed model into one model, that is partially premixed model. So let's go to Fluent GUI and start the pre-processing. Okay, so here we have imported this mesh, and here after zooming we can see how fine this mesh is at the inlet and the outlet conditions. So we will check for the quality. So the quality is fine, then we have to go for report quality. So report quality is done. We'll be using pressure based and steady. So here we are using axisymmetric swirl. So we will change it to axisymmetric swirl condition. Then we have to go into models. Models, we will turn on K epsilon model. We'll be using K epsilon turbulence model for our calculations. Then we will go for OK. In species, we have to go and we have to check for partially premixed combustion model. So here, as we have seen in the steps, that we will be using C equation model, and for chemical equilibrium, so here we'll be using fuel stream rich flammability limit to 1. Changing this value means that fluent will perform equilibrium calculation at all mixture fractions, that is 1 being the largest possible fraction. So if this was not the case, the composition would be computed based on the mixing instead for fractions above the specified value. So that's why we are keeping this fuel stream rich flammability limit to 1. Then we have to go and we have to change the bond ring. So here we'll be using methane as we discussed. So we have to give methane N2 and O2's mass fraction values for fuel here. And as we are using a lean combustion, so we'll be dealing with 0.8 stoichiometric ratio. So for 0.8 stoichiometric ratio, the concentration of fuel to be used in mass fraction is 0.0453, and for N2 it is 0.7283, and for last, that is for oxygen, it is 0.2264. So everything is done. Just one thing, oxidizer, the air will be entering at air inlet value, it is 650 Kelvin. So we have to change this value here, and if any more species if we want to add, we can add using this, but for our simulation we will be using CH4. Then we have to go in control, we don't have to change anything, in flamelet nothing. In table we have to calculate our PDF table. So the PDF table has been calculated successfully. We will go into properties and we will just check for laminar flame speed, how it is varying. So here we can see that for a single mixture fraction, the laminar flame speed is automatically calculated by the PDF table which we just generated. So for the simulation, it will use this laminar flame speed at different conditions. Here even we can check for adiabatic unburnt temperature, how it varies. These are the coefficient which will be used. So we have to click apply, then we go for OK. So here we have these all options if one want to use. So we won't be using those now. So we'll go into materials. In materials, so if we go into this PDF mixture, here we can see for mixture density it is PDF, then CP and everything. We go into laminar flame speed, this pre-PDF polynomial as we saw earlier. So unburnt CP and adiabatic unburnt temperature and everything. Change create. Then we will go for boundary conditions. So here specifying boundary conditions, as I said, is very important. So air inlet, for air inlet we'll be using velocity inlet. Then we will change this magnitude normal to boundary to components. So we'll be using components here. So the axial velocity for which the air is entering is 10 meter per second, and then for specification method we will change it to intensity and hydraulic diameter, and this we will change turbulent intensity, we will change to 10%, and this we will change to 0.0254. Then in species, as this is air inlet, so we don't have to specify any of these values. Then we will go for fuel inlet. So this fuel is entering in as co-flow. Even here we will change this to components, and then we have to give axial velocity of 50 meter per second and swirl velocity of 30 meter per second. So even this we will change to intensity and hydraulic diameter. So the intensity again here will be 10%. Hydraulic diameter we will change. Hydraulic diameter again here will be 0.0254. So here this is fuel inlet. So we have to specify the mixture fraction here. Mean mixture fraction, which will be 1. Then progress variable will be 0. So we will click OK. In outlet, we have to see it is pressure outlet. We don't have to set any pressure values here though. We will go into intensity and hydraulic diameter as we have specified for all of them. So this we will change again to 10%, and hydraulic diameter we will be changing it to 0.13. As the length is 0.15, we can use a smaller diameter for that. In species, we just have to go and we have to specify progress variable of 1 because that is outlet. We'll go for OK. So axis and symmetry, it will take everything automatically. We don't have to worry about that. Then we will go in directly into methods. In methods, we will change this to simple as we are using steady state calculations, and we just have to change everything to second order up and here. Just make sure we get convergence for our solution. Then we have to go into controls. In controls, we can select what all equations we'll be using. So till now we have discussed we have to resolve a cold flow simulation, and then we have to go for hot flow. So I'll show you how we can do that. So here we just have to unselect this PDF and premixed combustion. So these things will solve the cold flow equations. So we will go for OK. Then we have to go into initialization, and this time we will go for hybrid initialization. Hybrid initialization is mostly used when we don't have a single inlet. So where multiple inlets are involved, we go for hybrid initialization. But Fluent itself initializes the values from where it should be initialized. Then we will go into run calculations, and we will set the equations to, let's say, 500. We will save the case 5 here and give a random name. We will save this case 5. Once the case is saved, we can go for calculate. So the calculation has complete, and we can see 500 equations are solved, and we can see how the residuals have varied, and only the swirl velocity, turbulence and continuity has been solved. So what we will do now is that first we will go and we will change the equations from these three to the next two. So we will go for hot flow conditions now. And then one more thing what we have to do is that we have to patch. So we will go into adapt, refine and coarsen, go into cell registers, new, then region. So we have to specify a small region near inlet where we can patch progress variable c equals to 0 value. We will select a small value of 0.1 as x minimum and this value as 0.14. So y will be 0 because we'll be starting from y, and this value will be 0.03 meter. So even we can say see this region here. So this will be the region which will be patched the value of 0. So we will give this save. So this region will be saved, and OK. So I'll minimize this window. Again we have to go into initialization, and we have to select patch. So we have to select here progress variable. So value will be 0, and for the region which we just made here, you have to patch. So the patching is done. You can see the cells are marked here. Then we don't have to initialize anything, and we just have to solve the equation. So we will run for more 500 equations. Here we can see our solution is converged, and we have given 500 iterations to solve, but it has finished at almost some 335 iterations. So we can go for post processing now. One more thing here to see in the residuals is that after that 500 iterations only, the next three equations are solved which we selected for the PDF and for the premixed combustion. So we will go into graphics and we'll check for contours. We will see some interesting contours here. We will check for, first we'll check for velocity. So velocity magnitude, we'll save display. So this is how the velocity is varying here. So as we gave velocity variation, we can see how much velocity it has went. Maximum velocity is 58 meter per second. Then we will check for filled. We will untick this and we'll see how it shows us. So this is how the velocity profile is maintained. Then we will just click it back. Then we will check for temperature values. So temperature we will plot here. This is the flame which is created here. So here the mixture is entering, the fuel is entering, and then even air is entering. So co-flow simulation we can see here, co-flow results we can see here. The value which it has reached is 1730 kelvins. We will check for total temperature as well. So for total temperature is varying the same way. Then we will go and check for species. So mass fraction of CH4. So CH4 is entering in this way, and then it is getting consumed where the air is getting interacted with because of the mixing where it is interacting. It is getting consumed. We will check for products, how products are formed. So CO2 we will check first. You can see CO2 is formed along this part where the combustion is happening. Also we will check for H2O, the formation of H2O. So H2O and CO2 will be the same. Then we will go for premixed combustion. We will check for progress variable. So progress variable we can see here in the values. So 0, that is 0 value is maintained at the inlet, and 1 value is maintained at the outlets. Again we can check for, let's say, turbulent flame speed. So turbulent flame speed is varying in this way. Then we will check for laminar flame speed. So this is how laminar flame speed is varying for this condition. That is product formation rate. So how products are forming. So this is the region where more of the products are formed completely because of the combustion. Then we will check for some more values. Let's say pressure we will check. So we'll check for the static pressure variation. We'll check for total pressure as well. Total pressure will be changing here because of the combustion which is happening. We'll just check for density and we will move forward. So this is how density is changing. You can see that unburnt mixture, that is the unburnt mixture, is having more density than the burnt mixture. Then we will close this. We will check for some vectors as well. So this is how the vectors are forming. We'll change this value to, let's say, 0.5. Okay, I need to reduce it more. I'll keep it 0.1. Okay, more 0.25, let's say. So if I keep 0.25, we can see how this region is forming here where the combustion is happening. So here the mixing is happening because of the axisymmetric swirl condition which we have given. So then we will close this and we will check for, let's say, path lines. So we'll check for velocity, or maybe we can check, okay, let's say velocity, air inlet and fuel inlet. So these are the path lines. We will see how they are moving here from here. We can see how the mixing is happening and then it is moving and the combustion is initiated. So we'll stop this and we will, maybe you can check for temperature. We'll see for temperature. We'll give pulse. Even here we can see how the mixing is happening at the region and then it is moving forward. We will go for some plots. We'll check for some XY plots here. Check for air inlet. We will plot pressure. We will compare it with the fuel inlet. So this will give fuel inlet plots. Then we'll check for velocity. This is velocity variation. We'll see for the temperature variation. So we'll check for some of the reports here. We will check for surface integrals. So surface integrals, we will check for some mass weighted average values for some of the things. So air inlet, we will check the static pressure, how much it is. Then for fuel inlet, so both of them are negative, but when we come for outlet, it will be 0 because the pressure change is happening here. A combustion wave is formed. We'll check for outlet density. We'll check for air inlet and we will check for fuel inlet as well. So this is the density variation. We'll check for velocity, how much velocity it has been given. So fuel inlet we give velocity, swirl velocity and an axial velocity. So the mass weighted average velocity which is the inlet has given is 58 meter per second. And for air inlet we gave 10, so it is 10. We'll see how it has varied for outlet. So it has varied to 11.7 meter per second. So we'll check for some temperature also. So static temperature we will check at our air inlet which we specified as 650 kelvins. Then for fuel inlet we specified as 300, but due to the co-flow and the air fuel mixing it has gone to 302 kelvins. For outlet it has reached to 1632 kelvins. So we can see the combustion has happened here. Then we will go and we will check for progress variable values as well. So there it is 0. Fuel inlet we will check, it should be 0. At outlet it should be 1 or nearly equal to 1. So it is equal to 1. So this way we have seen how partially premixed combustion model works, and also we have seen how we can simulate a cold flow simulation first and then a hot flow simulation. So this was all about partially premixed combustion model where we can simulate such kind of problems which involve both premixed as well as non-premixed combustion. So the summary for today's class is that we have discussed what is partially premixed combustion model. So these partially premixed combustion systems are nothing but premixed flames with non-uniform fuel oxidizer mixtures, and that's why this partially premixed combustion model in ANSYS Fluent is a combination of both premixed and non-premixed combustion models. Then we have seen some examples of this system that are premixed jets discharging into quiescent atmosphere, then lean premixed combustors with diffusion pilot flames. Then we have seen two types of partially premixed combustion models are offered by ANSYS Fluent, that is thin flamelet model and flamelet generated manifold. Again, we have seen some limitations of partially premixed combustion model. That single mixture fraction approach is limited to two inlet streams, which may be pure fuel, pure oxidizer, or a mixture of fuel and oxidizer. Then we have seen a demonstration of partially premixed combustion model using an example. So the references for today's class are present here. In next class, we will start with post-processing of combustion results. Thank you.